Scattered across a vast desert lies a field of glass forged from pure sand. This is the Libyan Desert Glass, a substance whose very existence points to a cataclysm of unimaginable force. By the end of this exploration, you will understand how a single natural event can rewrite our perception of Earth's violent history. The glass formed under heat, rivaling the surface of a star, yet no crater marks the spot. Could this be the lingering scar of an ancient atomic event, or something even stranger from the cosmos? What does our fascination with this mystery reveal about our own place in a deep and unpredictable past? Millions of years before the first human eye glimpsed its glow, the stage was set within a crushing emptiness. The Great Sand Sea stretches across eastern Libya and western Egypt, a true ocean of sand where temperatures soar and life retreats. This is a landscape defined by absence, by wind and sun, and an almost planetary silence. Yet, scattered like shattered jewels upon this vast, tan canvas, lie fields of a substance that seems utterly out of place. Shards of canary yellow glass, some as large as bricks and weighing over 25 kilograms, gleam under the relentless sun. This is Libyan desert glass, and its very presence here is the first profound clue. It is not a handful of fragments, but a distribution across thousands of square kilometers, a littering of brilliance across a continental scale. This immediately tells us something crucial. No ancient furnace, no human workshop could ever produce such a staggering volume of material over such an immense area. The origin event was not local or artisanal. It was catastrophic, an instant of transformative power that marked the land itself. Scientifically, the glass is astonishingly pure, consisting of over 98% silica, which gives it that captivating, vitreous luster. It feels cool and smooth to the touch, a permanent tear of solidified light. So here we have our crime scene, stark and beautiful, a vast desert, and within it, a cryptic substance born of impossible heat. The stage is set, but the players and the plot remain a mystery written in fire and sand. That glass holds a thermal memory, a silent record of the inferno that birthed it. To understand the scale of the event, we need to grasp the sheer intensity of the heat involved. Think of a common campfire where temperatures might reach around 600 degrees Celsius, hot enough to char wood and warm the air. A volcano, one of Earth's most powerful natural forces, can produce lava that flows at temperatures between 700 and 1200 degrees, melting rock into the dark, glossy glass we call obsidian. This is the baseline for most natural glass formation on our planet. Libyan desert glass exists in a completely different league. Its internal structure, the way its molecules are arranged, tells a story of temperatures soaring between 1,600 and 2,200 degrees Celsius. To put that into perspective, that is hotter than the melting point of iron, hotter than the inside of a blast furnace in a modern steel mill. It approaches the surface temperature of some stars. At this level of thermal fury, the very physics of the event changes. Ordinary sand doesn't just melt into a gooey liquid, it undergoes a violent transformation. The silica grains are flash-heated so intensely that they vaporize, turning into a superheated gas, a plasma of silicon and oxygen. Then, in an instant, this cloud of vapor must have cooled rapidly, condensing back into a solid without ever passing through a familiar molten state. This process creates the glass's remarkable purity and its unique, homogeneous structure, with no crystalline grains like you'd find in slowly cooled rock. This thermal fingerprint is the first undeniable clue that something truly extraordinary happened. It wasn't a slow geological bake, it was a sudden, astronomical flash. A pinpoint strike of energy so concentrated it left this permanent scar upon the land. The question now becomes terrifyingly simple. On the surface of our ancient Earth, What natural force could possibly deliver such a star-forged kiss of heat? That thermal fingerprint points to a cosmic event, but the next clue complicates the story dramatically. In any classic investigation, the absence of expected evidence can be just as telling as its presence. If a massive meteorite, a mountain of rock and iron from space, had slammed into this desert to generate such heat, physics dictates a very specific aftermath. The incredible force of the impact would vaporize the meteorite and a vast amount of the ground beneath it, blasting a colossal hole into the Earth's crust. We see this pattern across our planet, from the famous Barringer crater in Arizona to the ancient, eroded scars hidden beneath forests and ice. The result is always a clear, circular depression, a crater, surrounded by fields of ejected debris and specific types of shocked rock. For the Libyan Desert Glass, such a crater would be the smoking gun. Yet, despite decades of searching with satellites scanning from orbit and teams walking the ground, no definitive impact crater of the right size or age has been found anywhere near the main glass fields. This is not a small missing detail, it is a gaping hole in the most straightforward explanation. The crater is conspicuously, puzzlingly absent. This forces a profound shift in thinking. If the heat did not come from below, from a ground zero impact, then perhaps it came from above. Could the source have been an object that never actually struck the Earth? One compelling theory suggests an airburst, a cosmic body that entered the atmosphere at a shallow angle and detonated in a titanic explosion several kilometers above the desert floor. The heat from such an event would have been a sweeping, radiant flash, instantly melting the sand across a vast area without ever concentrating its force into a single, deep pit. This would explain both the widespread distribution of the glass and the missing crater. It paints a picture not of a localized strike, but of a sky suddenly turning into a furnace, a horizon-to-horizon instant of star-like heat that then vanished as quickly as it appeared. The absence of the crater, therefore, isn't an end to the mystery, but a doorway into considering events of even greater scale and strangeness. What could deliver such a devastating aerial blast, and are there other echoes of this event hidden in the geological record? The most compelling answer science can offer today points not to the ground but to the sky. The leading hypothesis for the creation of the Libyan Desert Glass is a cosmic airburst, an event of almost unimaginable violence. Picture a comet or asteroid, a mountain of ice and rock hurtling through space on a collision course with our atmosphere. Instead of striking the surface, it meets the thickening air at a shallow angle, compressing and heating until it can take no more. The entire object detonates in a colossal fireball several kilometers above the desert, releasing energy thousands of times greater than the atomic weapon used at Hiroshima. This is not a slow burn, but a single, devastating flash. The radiant heat from this aerial explosion, lasting mere seconds, would have been enough to instantly fuse the sand across thousands of square kilometers into a sea of glass. The subsequent shockwave, a wall of superheated, compressed air racing outward at supersonic speeds, would have scoured the landscape clean, explaining both the vast distribution of the material and, critically, the absence of a traditional crater. The force was applied like a blowtorch held over a wide area, not a hammer striking a single point. We have a terrifying modern analog for such an event. In 1908, over a remote forest in Siberia, an explosion flattened 80 million trees across 2,000 square kilometers. The Tunguska event, as it's known, is widely believed to have been an airburst. Yet, to create the Libyan Desert Glass field, the event over the Sahara would have needed to be hundreds, perhaps thousands of times more powerful. The physical evidence locked within the glass itself supports this cosmic origin. Researchers have identified microscopic grains of minerals like rhyodite, a form of zircon that only forms under the staggering pressures generated by hypervelocity impacts. These tiny, durable crystals are like forensic fingerprints, confirming that the sand endured a shockwave of extraterrestrial magnitude. This hypothesis grounds the mystery in a terrifying but natural astronomical process. It transforms the desert glass from a cryptic artifact into a monumental warning sign, a permanent record of our planet's vulnerability to celestial threats. It suggests that our world's history is punctuated not just by the slow grind of geology, but by sudden, catastrophic gifts from the void. If this is the answer, it raises an even deeper question. Could such an event have been witnessed or even survived by the early humans who later wandered this same desert? Yet this scientific explanation has not been the only voice in the conversation. There exists a far more controversial interpretation, one that steps beyond natural astronomy and into the realm of lost history. This is the ancient atomic war theory, a speculative idea that suggests the glass is not a natural warning but a technological relic. Proponents of this view look at the same evidence, the intense heat and the missing crater, and ask a different question. Could this be the signature of a weapon rather than a random cosmic accident? They draw parallels to the fused sand found at nuclear test sites in the 20th century, where the first atomic detonations created thin layers of glass called Trinitite. The visual similarity is striking, and it presents a haunting analogy. If a mid-20th century bomb could fuse sand in the Nevada desert, what could a far more powerful device have done in the ancient Sahara? This line of thinking often connects to interpretations of certain ancient texts, like the Hindu epic the Mahabharata, which contains passages describing weapons of catastrophic light and heat, blasts that could level cities and leave the land sterile. From this perspective, the Libyan desert glass becomes potential physical evidence for a narrative of a forgotten advanced civilization, one that possessed, and perhaps tragically used, technology of unimaginable scale, only to vanish and leave behind only this cryptic, glowing scar as a monument to their passing. Mainstream archaeology and history firmly reject this theory, citing a complete absence of corroborating evidence. No cities, no tools, no cultural layers, nothing that indicates a society capable of such engineering exists in the geological record of that time and place. The theory persists, however, not because of its scientific rigor, but because of the powerful human questions it forces to the surface. It directly confronts the unsettling puzzle of the missing crater by proposing an intelligent source for the heat, a directed event. More deeply, it challenges the linear narrative of human progress, whispering the possibility that our history might be a cycle of rise and cataclysm, rather than a steady climb. While the atomic war theory remains firmly in the category of speculation, its enduring appeal lies in this very function. It acts as a mirror, reflecting our own modern anxieties about technological power and societal fragility back onto the deep past, and in doing so, it compels us to honestly examine the limits of what we truly know about the story of our world and our place within it. The glass itself is a time capsule holding microscopic evidence of its violent birth. To move beyond speculation and into the realm of forensic science, we must look deeper than its smooth surface, into its very atomic structure. Within the yellow glass, researchers have found two key components that act as precise thermal recorders. The first is a mineral called zircon. Under normal conditions, zircon is incredibly durable, a tiny timekeeper that can survive for billions of years. But within the Libyan desert glass, these crystals tell a different story. They have been found partially decomposed, transformed into a different mineral known as baddelite. This chemical change is not a subtle one. It is a metamorphosis that requires sustained temperatures exceeding 1,750 degrees Celsius. That number alone narrows the field of possible causes dramatically, ruling out all but the most extreme events. The second piece of evidence is even more striking. Scattered throughout the glass are peculiar bubbles or inclusions of a substance called lechatelierite. This is not a mineral in the traditional sense, but a form of pure fused quartz glass. It forms in one specific way when grains of quartz sand are heated so rapidly and so intensely that they vaporize and then re-solidify almost in the same instant, a process requiring temperatures above 1,600 degrees. Think of it like this: if you slowly heat butter in a pan, it melts. But if you toss it into a blast furnace, it vanishes in a puff of smoke and leaves behind only a residue. Lechatelierite is that residue, the ghost of sand that was flash vaporized. These microscopic features are the frozen signatures of an event measured in seconds. They are not the product of a slow geological bake like lava flowing over a beach. They are the indelible marks of a sudden, apocalyptic flash of heat, a thermal spike of astronomical proportions. This forensic analysis provides the non-negotiable data that any theory, whether it points to a cosmic airburst or something more speculative, must ultimately explain. The mystery is no longer just about where the glass is, but what these tiny, trapped witnesses insist happened to it. 29 million years is a span of time that defies easy comprehension. To place this event, we must step into a world unrecognizable. The late Oligocene epoch was a planet in transition. The great dinosaurs had been gone for over 30 million years, their reign replaced by the rise of mammals. Early ancestors of elephants and horses roamed forests and grasslands, while the continents continued their slow, imperceptible drift toward their modern positions. Crucially, the Sahara Desert as we know it did not exist. The region was likely a mosaic of savannas and woodlands. This is the temporal stage upon which our cataclysm occurred, a world without a single witness that could record it in memory or myth. Scientists arrived at this astonishing date not by guesswork, but through the silent, steady clocks locked within the glass itself. Techniques like fission track dating count the microscopic damage trails left by the spontaneous fission of uranium atoms within mineral grains, while potassium-argon dating measures the decay of radioactive potassium into argon gas. These methods do not rely on human interpretation of layers. They listen to the atomic decay that has ticked away since the moment the glass solidified. The consistent result, approximately 29 million years, is a robust scientific anchor. This date does one very clear thing. It completely separates the formation of the glass from the entire timeline of human civilization, or even proto-human evolution. Our earliest hominin ancestors would not appear for another 25 million years. This chronological fact is the definitive argument against the ancient atomic war theory, as it places the event in a deep prehistory where no intelligence capable of such technology existed on Earth. The mystery, therefore, is not a human one but a purely planetary and cosmic story. Yet this firm dating introduces a new and profound puzzle of its own. If an airburst or impact of such colossal energy occurred, one powerful enough to fuse thousands of square kilometers of terrain, why is its signal not more starkly written in the global geological record? Where are the widespread layers of dust, the telltale chemical signatures in ice cores or ocean sediments that mark other known extinction-level events? The answer may lie in the very nature of an airburst. Unlike a ground impact that excavates and throws millions of tons of pulverized rock into the stratosphere to circle the globe, an aerial explosion might deposit far less material into high-altitude wind currents. Its most dramatic effect, the radiant heat, would be terrifyingly local, scorching the surface but potentially leaving a fainter global fingerprint. The desert glass thus becomes a monument to a specific type of catastrophe, one that leaves a glaring, localized scar but a whisper in the broader chapters of Earth's history. It forces us to consider how many other such events, terrifying and transformative for their immediate region, might have occurred and then been slowly erased by the relentless work of wind, water, and time, leaving no trace behind except perhaps for a single, inexplicable field of yellow glass under an endless sky. The story of this ancient glass finds strange echoes in other objects born from celestial and human fire. Scattered across parts of Europe, particularly the Czech Republic and Germany, lie pieces of a beautiful, translucent green glass called moldavite. These are tektites, natural glasses formed when a massive meteorite impact melts terrestrial rock and hurls it high into the atmosphere, where it cools and rains down over a vast area known as a strewn field. While tektites and the Libyan Desert Glass share a cosmic origin story, they are distinct cousins. Tektites are typically smaller, darker, and contain more impurities from the rock they were blasted from, telling the story of a violent launch and a long fall. The desert glass, by contrast, is purer and rests directly where it formed, a product of sand fused in place by radiant heat, not of material thrown across a continent. This distinction is crucial. It points to two different kinds of cosmic violence, one that excavates and scatters, and another that simply, utterly melts. But the most provocative comparison lies not in the ancient past, but in the modern era. In July of 1945, the first test of an atomic weapon, code-named Trinity, fused the desert sand of the New Mexico test site into a thin, crusty layer of green glass. This material was later named Trinitite. When scientists examined Trinitite and the Libyan desert glass side by side, the morphological and structural similarities are deeply arresting. Both were created in an instant of apocalyptic heat, both capture that moment in a vitrified form, and both exhibit the unique bubbles and textures of sand flash fused into a solid. Trinitite serves as a powerful, sobering analog, a controlled experiment from our own time that demonstrates unequivocally how atomic-scale energy can transform a landscape. This comparison does not, in itself, prove an ancient atomic event. What it does is provide a tangible, scientific bridge. It shows that the processes required to create the desert glass are not purely theoretical or locked in the distant cosmos. They are processes humanity has now harnessed and witnessed. This parallel inevitably fuels speculation, forcing a haunting question. If we, in the mid-20th century, could create a small patch of desert glass with a single device, what unimaginably larger natural event could have once painted an entire region with the same terrible, brilliant stroke? The ancient glass waited in silence for epochs, but its story did not end with its formation. It was found. Long before modern science sought to explain its origin, human hands reached for its luminous beauty. One of the most direct and stunning connections lies in the treasure-filled tomb of the boy King Tutankhamun. Among the exquisite artifacts buried with him over 3,000 years ago is a pectoral necklace, a ceremonial piece meant to adorn his chest for eternity. At its center sits a large carved scarab beetle, a symbol of rebirth and the sun. This scarab is not made of jade or lapis lazuli, but of a distinctive, translucent yellow stone. Scientific analysis has confirmed it is a piece of Libyan desert glass, meticulously shaped and polished by ancient artisans. This single object tells a profound story of human curiosity and value. It means that over 3 millennia ago, people were undertaking perilous journeys across the vast and deadly Great Sand Sea, a place of extreme heat and shifting dunes, to collect this mysterious material. They did not know it was 29 million years old. They only knew it was unlike anything else they possessed. Its radiant color, its cool smoothness, and its origin in a place of such hardship would have imbued it with immense significance. To the ancient Egyptian mind, such a substance, born from the desert under the blazing sun god Ra, likely held profound mystical or divine properties. It was a piece of the sun's own fire made solid, a perfect material for a scarab representing solar rebirth. This cultural footprint transforms the glass from a mere geological oddity into a bridge across human time. It invites us to wonder about the myths they constructed to explain its existence. Did they believe it was the tears of a god or the solidified light of a fallen star? Their act of collection and reverence adds a rich human layer to the mystery, reminding us that long before we sought to analyze the glass, we were drawn to its story, seeking to give meaning to the inexplicable wonders of our world. The scarab in Tutankhamun's tomb connects us to the glass through wonder, but science must connect it through a landscape of pure devastation. To truly grasp the event that created it, we must move beyond the moment of the flash and walk through the world it left behind. The leading theory of a cosmic airburst paints a picture of an environmental cataclysm almost beyond description. First, the light. A fireball tens of kilometers wide would have bloomed in the sky, outshining the sun itself for a terrifying instant. This radiant pulse of heat, lasting mere seconds, was the artist that painted the desert with glass. But its work was just beginning. That sudden, incredible heating of the atmosphere would have triggered a physical reaction of colossal violence. The air itself, superheated and expanding faster than the speed of sound, would have generated a shockwave of unimaginable force. This wall of compressed energy would have raced outward across the ancient savanna, not as a gust of wind, but as a bulldozer of pure pressure. It would have flattened every tree, scoured the soil from bedrock, and pulverized rock into dust for hundreds of kilometers in every direction. Following this initial blast front would come hurricane-force winds, rushing in to fill the temporary void, carrying with them a torrent of superheated sand and debris, sandblasting the landscape a second time. Every living thing within the immediate zone, for perhaps 200 kilometers, would have faced instant, total loss. The regional ecosystem would have been erased in a geological instant. The consequences would then have rippled outward. A vast plume of dust, ash, and vaporized rock, lifted high into the stratosphere by the explosion's thermal column, could have circled the globe. This atmospheric shroud would have blocked sunlight, potentially triggering a period of global cooling, an impact winter that might have lasted for years. While this single event 29 million years ago likely wasn't severe enough to cause a mass extinction on the scale of the dinosaur-ending asteroid, it would have been a severe regional catastrophe with global climatic echoes. Scientists use sophisticated computer models to simulate these aftermaths, not out of morbid curiosity, but to understand the full spectrum of threats our planet faces. The Libyan Desert Glass, therefore, is more than a mineralogical curiosity. It is a benchmark. It provides a real-world data point against which to calibrate these models of cosmic violence. It reminds us with silent, yellow clarity that Earth's story is not one of serene, gradual change. It is a biography written in long chapters of stability, punctuated by sudden, violent sentences of fire and ice from the cosmos. This understanding shifts our perspective from a single mystery in the sand to a sobering lesson about our planetary home's place in a dynamic and sometimes dangerous solar system. The mystery is not locked in the past, it is actively being pursued under the desert sun. Modern scientific missions continue to trek into the Great Sand Sea, a testament to the enduring power of this enigma. These are not casual surveys, but carefully planned expeditions that must contend with one of the most punishing environments on Earth. Temperatures that can scorch past 50 degrees Celsius, shifting dunes that swallow landmarks, and a profound isolation make every journey a logistical challenge. Yet scientists return, driven by the promise held within those scattered, yellow fragments. Their goal is to move the investigation from broad theories to precise, granular understanding. This work involves creating high-resolution maps of the glass distribution, which is far more complex than a simple, even blanket. Where are the thickest concentrations? Are there patterns or gradients that might point toward a directional blast or multiple epicenters? Answering these questions requires walking the ground, often with the aid of drone technology that can scan vast areas from above, revealing patterns invisible at human scale. Each expedition also seeks pristine samples, pieces of glass untouched by the weathering of millennia or the hands of ancient collectors. Using portable analytical labs, researchers can now perform initial chemical and structural tests right there in the field. They search for microscopic forensic evidence that might have been overlooked, such as specific forms of shocked quartz, which bears the unique deformation patterns of a hypervelocity impact, or tiny spherules of impact ejecta, microscopic droplets of melted rock that could hold a chemical signature of the impacting body itself. The hope is to find a definitive geochemical fingerprint, perhaps an isotopic ratio, that can finally identify the culprit, whether it was a stony asteroid, an icy comet, or something else entirely. This ongoing work demonstrates a crucial point about the Libyan Desert Glass. It is not a solved puzzle sitting quietly in a museum display case. It represents an active, evolving frontier in planetary science and geology. Every new data point from the sand, every grain analyzed under an electron microscope, adds another piece to a chronological sequence that stretches from a quiet ancient landscape to a sky-shattering instant and its long, silent aftermath. The story is being written and revised with each expedition, reminding us that some of Earth's greatest mysteries are still out there, waiting in the most desolate and beautiful places for the next curious mind to ask the right question. These silent yellow fragments hold a hidden language, one we have learned to read through light itself. To move from broad theories to precise, undeniable facts, science turns to a powerful family of tools called spectroscopy. This is the art and science of asking the glass what it is made of by listening to how it interacts with energy. Imagine for a moment that every element in the universe has its own unique song, a specific frequency at which it vibrates. Spectroscopy is the method of gently probing a material with a precise form of energy, like X-rays or a laser beam, and then carefully analyzing the response, the unique song it sings back. One common technique is X-ray fluorescence. When a handheld spectrometer is pointed at a piece of the desert glass, it bathes the sample in a safe, low-energy X-ray beam. This energy excites the atoms within the glass, causing them to emit their own characteristic X-rays as they settle back down. A detector then reads this emitted signal. Each peak and valley in the resulting graph corresponds directly to a specific element, like silicon or oxygen, and its precise abundance. The readout is stunningly clear, showing a composition of over 98% silica, with only the faintest traces of elements like aluminum, iron, or sodium. This exceptional purity is the first major data point, confirming this is no ordinary volcanic glass or human-made slag. Another powerful method is mass spectrometry, which takes a tiny, almost invisible sample and vaporizes it into a cloud of charged particles or ions. These ions are then sorted by their mass and charge as they fly through a magnetic field, creating an exquisitely detailed breakdown of the sample's atomic makeup, down to the isotopic level. Isotopes are different versions of the same element with slightly different atomic weights, and their ratios can act as a forensic tracer. The chemical fingerprint produced by these techniques is the glass's immutable identity card. Scientists can then perform a direct comparison. They take samples of ordinary sand from the Great Sand Sea and subject them to the same spectroscopic analysis. The results show a near-perfect match in major elements, conclusively proving the glass was indeed born from the local desert floor. It is transformed sand, not an imported substance. But the comparison goes further. This same chemical fingerprint can be stacked against the profiles of known impact materials from confirmed craters around the world, or against the composition of different types of meteorites. The goal is to find a match, to see if the trace elements and isotopic signatures in the glass point toward a specific type of cosmic culprit, like a carbonaceous chondrite asteroid or a stony iron body. This data is objective, quantitative, and irrefutable. It forms the non-negotiable bedrock of the investigation. No theory, whether it champions a comet, airburst, or speculates about more exotic origins, can stand if it contradicts the fundamental story told by the glass's own elemental voice. In this way, spectroscopy transforms a beautiful mystery into a solvable equation, written in the silent language of atoms. Yet this scientific clarity requires us to confront the powerful allure of the alternative. The idea of an ancient, lost civilization wielding atomic power is a narrative of profound resonance. It speaks to our fears about our own technological trajectory and our fascination with forgotten golden ages. It transforms the desert glass from a natural oddity into a tragic monument, a warning from a deep and cyclical past. The theory is compelling precisely because it personalizes the cataclysm, giving it an author and a motive where nature offers only random chance. However, a rigorous investigation must weigh narrative satisfaction against evidential bedrock, and here the ancient atomic war theory encounters insurmountable obstacles. The most definitive is the one we've already anchored, the 29-million-year age. This date, derived from atomic clocks within the glass itself, places its formation in an epoch when the most advanced life on land were early mammals. No primate walked the earth, let alone a species capable of advanced engineering. This single fact severs the glass from any conceivable human history. Furthermore, if such a technologically advanced society existed, its footprint would be monumental, not cryptic. Where are the vitrified cities, the stratified layers of advanced tools, the evidence of mining, metallurgy, or large-scale construction that would accompany such power? The archaeological record of North Africa, while rich with human history stretching back millennia, shows a continuous, understandable progression of technology, with no sudden, anomalous leap or subsequent void that would indicate a prior, fallen civilization. The glass field stands alone, a singular phenomenon without the supporting context of a society that could have created it deliberately. Even the haunting parallel to Trinitite, the glass from the atomic test, ultimately argues against the theory. Modern Trinitite contains specific radioactive isotopes, unique signatures of fissionable materials like plutonium, that are utterly absent in the Libyan desert glass. Its radioactivity is negligible, identical to natural background levels. The processes may look similar in their thermal effects, but their nuclear fingerprints are completely different. This process of separating fact from compelling fiction is not an exercise in dismissing wonder. It is the essential work of grounding our curiosity in reality. It applies a principle known as Occam's razor, which suggests that among competing hypotheses, the one with the fewest assumptions is often preferable. The Airburst hypothesis, while still containing unanswered questions, requires no assumptions about unknown civilizations or lost technologies. It operates entirely within the established frameworks of celestial mechanics, impact physics, and Earth's known geological history. It fits the evidence, the age, the chemistry, and the distribution without needing to invent a grand, unproven backstory. Choosing this scientific path does not make the story any less astonishing. In fact, it may make it more profound. It tells us that the universe itself, through the random, majestic violence of comets and asteroids, is capable of writing the same apocalyptic signature upon our planet that we once believed only our own hands could craft. The truth removes a human author, but in doing so, it reveals a cosmos of far greater and more humbling scale. The story of this desert glass is not confined to our world. Its narrative extends into the solar system, offering a key to unlocking histories written on other planets. On Mars, the stark red landscape holds its own cryptic signatures of violent transformation. NASA rovers trundling across that distant surface have identified intriguing deposits within Martian craters, materials that spectral analysis suggests are likely impact glass. These formations are believed to be the frozen remnants of ancient meteorite strikes, moments when the Martian ground was flash-heated and fused, much like the sands of the Sahara. This discovery creates a profound scientific bridge. By comparing the Libyan desert glass on Earth to similar formations on Mars, researchers can begin to build universal models for how such materials behave under wildly different conditions. They can ask new questions. How does a thin, carbon dioxide-rich atmosphere like that of Mars affect the dispersal of heat and ejecta from an impact compared to Earth's thicker nitrogen-oxygen shield? How does the weaker gravity of the red planet influence the way melted material cools and solidifies? Our desert glass provides the foundational, hands-on reference point, the detailed case study from a world we can physically visit and sample. It acts as a Rosetta Stone for interpreting the more fragmentary data sent back by our robotic explorers millions of kilometers away. This extraterrestrial connection fundamentally reframes the significance of those yellow shards. They are no longer just a fascinating regional mystery or a beautiful artifact for pharaohs. They become a calibrated instrument, a benchmark of catastrophic physics. Understanding their full story here allows us to read the more cryptic records left on Mars, Venus, or the moons of the outer planets. It transforms a patch of desert into a planetary laboratory, reminding us that the forces that shape worlds are both terrifyingly destructive and brilliantly creative, leaving behind signatures of fire that we are only just learning to translate across the deep silence of space. That psychological pull toward a lost civilization is not a modern invention, but a timeless human impulse. Across cultures and centuries, we have told stories of golden ages, of Atlantises and sunken continents, where wisdom and power exceeded our own. These narratives fulfill a deep need, offering an explanation for the ruins we find and a cautionary tale for the heights we might reach. The theory of an ancient atomic war fits perfectly into this archetypal mold. It transforms the Libyan desert glass from a random natural event into a profound symbol, a physical relic of a moral fable. The story warns of a cycle where technological advancement without wisdom leads inevitably to a fall. This resonates so powerfully today because we see our own reflection in it. We live in an age of staggering technological leaps, where artificial intelligence, genetic engineering, and yes, nuclear arsenals grant us powers that feel almost mythic in their scope. The haunting question of whether we are mature enough to wield such forces is not abstract, it is a daily headline. When we look at that glass and entertain the idea that it might be a weapon scar, we are not just pondering the past, we are projecting our own deepest anxieties onto the canvas of deep time. The desert becomes a screen, and the glass a focal point for our collective unease about progress, responsibility, and survival. This psychological layer explains why the theory persists despite the scientific evidence to the contrary. It is not competing on the same factual field, it is operating on the level of myth and meaning. The glass functions as a kind of Rorschach test for our relationship with history and the future. One person sees a scientific puzzle, a natural record of cosmic violence. Another sees a tombstone for a forgotten world, a direct warning from our own possible fate. This duality is what makes the subject so endlessly engaging. It forces us to confront why we are drawn to certain stories and what those stories reveal about our hopes and fears. The enduring mystery of the glass, therefore, is not just about what happened 29 million years ago. It is equally about why, thousands of years after a pharaoh wore it as jewelry, and decades after science dated its origin, we still feel the need to weave such a potent human drama around its silent, yellow glow. The same luminous beauty that drew ancient pharaohs now places this natural wonder in a modern dilemma. Beyond its scientific significance, the Libyan desert glass possesses an undeniable aesthetic allure, a radiant yellow clarity that has caught the eye of a global market. This has transformed the silent desert field into a resource, and like many rare resources, it has become entangled in a complex struggle between preservation and profit. Illegal harvesting operations, often under cover of darkness, venture into the remote desert to collect large quantities of the glass. These pieces are then cut, polished, and sold as exotic gemstones or mysterious artifacts to collectors around the world, commanding high prices for their otherworldly origin story. Each piece removed for a necklace or a private cabinet represents a profound loss for science. A shard taken from its precise location erases its contextual map, destroying vital information about distribution patterns, layering, and its relationship to the surrounding geology. It is like tearing a single, crucial page from a vast and ancient book before we have fully learned to read it. The commercial pressure creates a direct tension where the glass's monetary value threatens its irreplaceable value as a planetary record. This challenge raises urgent questions about stewardship. How do we protect a site so vast and remote? Who has the right to benefit from a natural wonder that belongs, in a sense, to both a nation and to human understanding itself? In response to this threat, concerted efforts are now underway by scientists and cultural heritage organizations to have the primary glass fields officially designated as a protected natural monument or UNESCO Global Geopark. Such a status would help regulate access, promote responsible scientific study, and potentially support controlled, sustainable ecotourism that educates rather than exploits. The goal is not to lock the desert away, but to safeguard it as a living laboratory and a place of inspiration. This ensures that future researchers, armed with ever more sophisticated tools, can return to this open-air archive, and that anyone captivated by the mystery can someday stand in that immense silence, not to take a piece, but to simply witness the enduring mark of a cosmic instant preserved for all. The silent glass fields pose a question that can only be answered through controlled recreation. To test the Airburst hypothesis, scientists do not just analyze the evidence, they attempt to rebuild the event itself, from the cosmic scale down to the atomic. This begins in the realm of digital simulation, where supercomputers run complex physics models. Researchers input variables like the estimated size of the incoming body, its composition, its speed, and its entry angle into Earth's atmosphere. The software then calculates the cascading chain of events. It visualizes how the immense pressure of atmospheric compression would cause the object to fragment and then catastrophically explode, not as a single point, but as a rapidly expanding fireball. The model tracks the propagation of the radiant heat pulse and the following shock wave, mapping how these forces would interact with the ancient terrain below. The goal is to see if a specific set of starting conditions can produce the exact outcome we observe, the widespread fusion of sand without a classic crater. These simulations are not mere animations, they are rigorous mathematical tests. When a model successfully reproduces the glass field's distribution and the missing crater, it strengthens the hypothesis, turning a compelling story into a quantifiable scenario. Yet a simulation is a theoretical construct, a prediction. To ground it in physical reality, science must go into the laboratory. Here, researchers employ a remarkable tool, high-powered lasers. They take small samples of pure silica sand and subject them to an intense, focused beam of light for a fraction of a second. This laser pulse delivers a microburst of energy so concentrated that it flash heats a tiny spot on the sand grain to thousands of degrees in an instant. The result is a minuscule bead or layer of freshly formed glass. Under powerful microscopes, scientists then scrutinize this lab-created glass. They examine its texture, its internal structure, the way bubbles form within it, and the specific minerals that crystallize out as it cools. Every detail is compared directly to the microstructure of the authentic Libyan desert glass. This painstaking comparison is a search for a match, a signature. If the glass created in the lab by a sudden, intense heat pulse bears the same microscopic fingerprints as the ancient desert glass. It provides powerful experimental confirmation of the proposed formation mechanism. These two approaches, the vast digital simulation and the pinpoint laboratory experiment, work in tandem. The models tell us the macro story of the cataclysm, while the laser experiments confirm the micro story of the material's transformation. Together, they build a bridge of understanding between the theoretical violence of a cosmic airburst and the tangible, beautiful, and enduring scar it left upon our world. This vast mystery cannot be confined to a single laboratory. Unlocking the story of the desert glass demands a rare convergence of minds, a symphony of scientific disciplines, each bringing its own essential instrument to the investigation. A geologist can describe the glass and map its location, but they cannot calculate the trajectory of a comet. An astronomer can model a catastrophic airburst, but they cannot analyze the microscopic chemistry of a fused grain of sand. A physicist can simulate the propagation of a shockwave, but they cannot interpret the cultural significance of a scarab in an ancient tomb. This puzzle exists at the intersection of all these fields, forcing experts who normally speak different technical languages to find a common tongue. The chemist, using tools like mass spectrometry, provides the non-negotiable elemental fingerprint, the what of the glass. The physicist and astronomer take that data and use computational models to propose the how, testing different celestial scenarios against the chemical and physical evidence. Then, entirely separate, the archaeologist and historian enter the conversation. They examine the human chapter of the story, tracing the journey of the glass from a mysterious desert object to a revered artifact in Tutankhamun's burial chamber. They scrutinize ancient texts not to take them literally as scientific reports, but to understand the mythological frameworks early cultures used to explain such wondrous materials. This interdisciplinary dance is the hallmark of how modern science tackles its grandest challenges. No single expert holds the entire truth. The solution emerges from the careful integration of disparate lines of evidence. The desert glass, therefore, is more than a geological specimen. It is a case study in collaborative discovery. It demonstrates that the deepest mysteries of our world often lie in the borderlands between established fields, waiting for us to build bridges of knowledge and listen to the full story told by the stones, the stars, and the silent records of human wonder. The scientific consensus points toward a cosmic airburst, yet the case remains stubbornly open. Despite decades of intense study, significant gaps in our understanding persist, each one a doorway to deeper inquiry. The most fundamental question is perhaps the most elusive. What exactly was the object that met its end in that ancient sky? Determining its precise size and composition is a monumental challenge. Was it a stony asteroid several hundred meters across, or a more fragile, icy comet nucleus that fragmented more easily in the atmosphere? The answer would dramatically alter our models of the event's energy and aftermath. The physical distribution of the glass itself presents another persistent riddle. The field is not a perfect circle or a random scatter. It shows a peculiar, somewhat elongated shape. This pattern could be a crucial clue, hinting at the angle of the incoming body or the direction of the ensuing fireball's expansion. Some researchers even propose a more complex scenario, suggesting that what we see today might not be the result of a single, colossal explosion, but perhaps a string of multiple, smaller airbursts from a fragmented comet, like a cosmic shotgun blast across the sky. This could explain both the concentrated patches and the overall stretched pattern of the debris. On a microscopic level, the hunt continues for the definitive smoking gun, a direct chemical fingerprint of the visitor. Scientists meticulously sift through the glass, searching for trace elements like iridium, which is much more common in asteroids and comets than in Earth's crust. They also analyze isotopic ratios, the subtle variations in atomic weight that can act as a celestial passport. Finding a clear signature of extraterrestrial material locked within the silica matrix would be the ultimate confirmation, directly linking the glass to a specific type of cosmic body. So far, such evidence has been tantalizing but not conclusive. Each of these unanswered questions represents a clear frontier for future research. They ensure that the Libyan Desert Glass will not simply become a closed chapter in a textbook. It remains a vibrant, active puzzle, drawing in new generations of geologists, planetary scientists, and chemists with ever more sophisticated tools. This enduring state of mystery is in many ways the greatest testament to the glass's power. It is a reminder that some of nature's most dramatic stories are not delivered to us fully explained. They are invitations. They ask us to keep looking, to keep questioning, and to remain comfortable with the beautiful uncertainty that lies at the heart of true discovery. Beyond the scientific journals, this yellow glass has found a vibrant second life in the stories we tell. Its enigmatic origin has made it a favorite subject in television documentaries and speculative series, where it is often presented as potential evidence for extraordinary theories about our past. You can find it discussed in passionate online communities dedicated to historical mysteries, where forum threads dissect every new research paper and every ancient text that might hold a clue. It has even inspired plot points in novels and films, serving as a physical MacGuffin that unlocks secrets of lost worlds or forgotten technologies. This cultural absorption is not trivial. It serves a powerful function by generating widespread public fascination, which in turn can help secure the funding and attention necessary for continued scientific fieldwork. A mystery that captures the imagination is a mystery that people are willing to support solving. However, this process inherently creates a fascinating tension. As the glass transitions from a geological specimen to a cultural symbol, the line between established fact and speculative narrative can become beautifully blurred. A television show might present the ancient atomic war theory not as a disproven idea, but as a tantalizing what-if scenario, emphasizing its dramatic power over its scientific shortcomings. This doesn't necessarily mean the public is being misled, but rather that the story is being used for a different purpose, to explore deeper questions about human history and potential. The journey of the Libyan Desert Glass from a silent desert field to a recurring character in our modern myths reveals something profound about how we process the unknown. We are not satisfied with data points alone. We instinctively weave narratives around them. We use story to give scale and meaning to events that defy simple explanation. The glass in its radiant silence becomes a perfect canvas. For the scientist, it is a record of atmospheric physics and celestial mechanics. For the storyteller, it is a relic of a lost age, a warning, or a key to a hidden chapter. These two approaches are not truly in conflict. They are complementary facets of the same human drive to understand. One seeks the objective truth of what happened, while the other seeks the subjective truth of what it means. The enduring popularity of the glass in culture ensures its mystery remains alive in the public mind, guaranteeing that the next generation of researchers will have an audience eager to hear what they find, and the next generation of dreamers will have a solid piece of reality on which to build new and ever more captivating tales. This single field of glass, resting under the Saharan sun for 29 million years, quietly dismantles the most comfortable assumptions about our place in time. For most of human history, our understanding of the past was measured in generations, in the rise and fall of empires, a timeline that felt vast to us but is, in geological terms, merely the blink of an eye. The Libyan Desert Glass introduces a different kind of clock, one that measures epochs in millions, not thousands of years. It forces us to confront the philosophical concept of deep time, a scale so immense it can feel like vertigo. To hold a piece of this glass is to hold a moment from a world where our species did not exist, where the continents were in different positions, and where the ancestors of today's elephants were small creatures in distant forests. This artifact does not fit into a human narrative. It predates every story we have ever told about ourselves. It is a relic from a chapter of Earth's autobiography, written long before the prologue of humanity began. This realization is profoundly humbling. It recontextualizes our entire history, not as the central plot, but as a recent, fleeting subplot in a much grander and more turbulent saga. The glass becomes a teacher of perspective, showing us that the ground we stand on, the very landscape we perceive as permanent, has been remade by forces of cosmic power. Our civilizations are built upon a stage that has been set and reset by events we are only beginning to comprehend. This shifts our understanding of planetary history from a slow, predictable grind, known as uniformitarianism, to a framework that must include catastrophism, the acceptance that sudden, violent upheavals are integral to the story. The desert glass is not an anomaly, it is a testament. It tells us that the calm periods we enjoy are the peaceful interludes between storms of celestial magnitude. Our planet's history is not a smooth line, but a series of long, quiet sentences punctuated by exclamation points written in fire and ice from space. To internalize this is to see the world differently. It means recognizing that the stability we rely on is not a guarantee, but a temporary gift. It invites a quiet awe, a respect for the dynamic and sometimes dangerous nature of our cosmic neighborhood. The glass, in its silent endurance, asks us to expand our sense of time, to consider our legacy not just in centuries, but in the context of millions of years, and to find both humility and resilience in that vast, beautiful scale. The allure of a forgotten atomic age speaks to something deep within us, a desire for a past more dramatic than our textbooks suggest. Yet this very appeal demands a careful ethical compass. How do we explore these captivating ideas without crossing the line into misinformation? The key lies not in silencing curiosity, but in framing it with intellectual honesty. Responsible engagement begins with a simple but vital practice, clearly labeling speculation for what it is. When we discuss the ancient atomic war theory, we should present it as a fascinating cultural narrative or a thought experiment, not as a hidden truth suppressed by mainstream science. This transparency respects the audience's intelligence, allowing them to enjoy the story while understanding its place in the larger puzzle. It is perfectly valid to ask, what if? But we must be equally forthright about the overwhelming weight of contrary evidence, such as the 29-million-year age that definitively separates the glass from human history. A balanced discussion acknowledges this evidence not as a conversation ender, but as the foundation that makes the mystery so profound in the first place. The most ethical approach is to pivot from pure speculation toward the real wonder, which is the rigorous scientific process itself. We can use the atomic war idea as a starting point to explain how researchers use spectroscopy to analyze chemical fingerprints, or how physicists model airbursts with supercomputers. This shifts the focus from an unproven conclusion to the thrilling methods of discovery. In doing so, the desert glass becomes a gateway to learning about planetary geology, cosmic threats, and the critical thinking skills needed to navigate a world full of extraordinary claims. The goal is to cultivate a sense of informed wonder, where we can appreciate the myth while marveling even more at the natural forces that are, in reality, far more astonishing. This ethical framework ensures the mystery remains a source of inspiration and education, a reminder that the true story of our planet, written in fire and glass, is compelling enough on its own. The final answer to this mystery is not waiting in a library, but in the tools we have yet to build. As powerful as our current science is, the next leap in understanding the desert glass will likely arrive on the back of technologies still emerging from laboratories or orbiting high above our atmosphere. Consider the very ground beneath the scattered shards. Could the missing crater be there after all, not as a surface bowl but as a deeply buried ancient structure, long since filled and hidden by 29 million years of shifting sand and sediment? Future generations of ground-penetrating radar, with exponentially greater resolution and depth penetration, could scan the desert's subsurface like a three-dimensional X-ray, searching for the telltale circular disruption in the rock layers that would signal a colossal, buried impact site. This would be a discovery that reshapes the entire narrative in an instant. At the atomic level, the hunt continues for that elusive cosmic fingerprint. The next wave of mass spectrometry instruments, with sensitivities we can barely conceive of today, might finally detect the unambiguous isotopic signature, the specific ratio of oxygen or silicon atoms that can only come from a comet or a particular type of asteroid. It would be the equivalent of finding a microscopic serial number on the culprit, ending the debate about its nature. Our perspective is also set to expand beyond our own planet. New space-based observation platforms equipped with hyperspectral sensors will methodically scan Earth's surface from orbit. Their precise eyes might identify other, previously unknown fields of similar glass in remote deserts from the Atacama to the Gobi. Finding a second or third site would transform this from a singular anomaly into a category of event, providing the comparative data needed to build a universal model for how such formations occur. This technological trajectory ensures the story of the Libyan Desert Glass is far from finished. Each new instrument, each more powerful way of seeing, promises not just incremental data, but the potential for a genuine surprise, a discovery that could once again overturn our most careful assumptions about that ancient, fiery moment. The glass has kept its secrets for millions of years, and it may only yield them fully to the curious minds and brilliant machines of a future we are just beginning to create. 29 million years of silence can be woven into a single, breathtaking moment. A comet, a mountain of ancient ice and cosmic dust, streaks into Earth's sky on a shallow, glancing path. The thickening atmosphere offers no gentle welcome. It is a wall of resistance. Stresses build, the immense structure cannot hold, and it shatters in a series of violent ruptures. Then, several kilometers above a savanna that would one day become the Sahara, the fragments unleash their stored celestial energy in a final, catastrophic release. The sky itself becomes a sun. For a few seconds, a radiative heat pulse, hotter than the inside of a blast furnace, washes across the land below. Every grain of silica sand on the surface absorbs this impossible energy, vaporizing in an instant before condensing back into a solid sheet of pure yellow glass. Following the light comes the thunder, a supersonic shockwave that races outward, scouring the landscape clean and distributing the freshly forged glass across thousands of square kilometers. There is no focused impact, no crater, only a wide, searing kiss from the heavens. This event, reconstructed from the chemical fingerprints and microscopic scars within the glass itself, aligns the forensic evidence with the unyielding laws of celestial mechanics. It is a story written in physics, yet the narrative does not end with the cooling of that glass. It patiently waits through ages of shifting climates until a new actor enters the scene. Millennia later, human eyes, drawn to its unearthly glow, find these scattered jewels. Without knowing their origin, they recognize their profound value. The glass is gathered, shaped, and placed at the heart of a pharaoh's journey to the afterlife, transforming from a geological record into a cultural treasure. This is the coherent thread that binds the mystery together, a synthesis of cosmic violence and human wonder. The remaining questions about the comet's exact size or the pattern of its fragments are not failures of the story, but invitations for its next chapter. They remind us that even our most elegant explanations are waypoints in a much longer journey of understanding. The shimmering fields of Libyan desert glass stand as a permanent question mark etched into our planet. They are a testament to a moment of apocalyptic violence frozen in time, a scar that refuses to fade. Whether formed by a terrifying cosmic airburst, a natural event of staggering scale, or, in the realm of human speculation, by forces we have yet to fully comprehend, this glass challenges us to expand our thinking. It asks us to look beyond the slow grind of geology and accept that our world's biography is written in both quiet paragraphs and sudden, fiery sentences delivered from the depths of space. This journey through science, myth, and enduring curiosity reveals more than the origin of a mineral. It reveals our own relationship with the unknown. We are drawn to the glass not just for what it is, but for the stories we can project upon its smooth surface, from pharaonic reverence to modern anxiety. It reminds us that our planet is still a place of profound mysteries, silent puzzles waiting in the most desolate places for the next generation of explorers, armed with new tools and fresh questions, to listen a little closer. What other secrets lie buried beneath the sands of time, or hidden in plain sight, waiting for a curious mind to connect the dots? The desert glass does not offer a final answer. It offers an invitation to keep looking upward and inward, to marvel at the forces that shape worlds and the human drive to understand them. If this exploration into deep time and celestial fire resonated with you, consider joining the conversation. Share your own thoughts on this mysterious glass in the comments below, and for more journeys into history's greatest enigmas, be sure to subscribe.